Now, as you know that we can categorize the solution depending upon that whether they obeyed Raoult's law at all condition of temperature or pressure, or whether they don't obey Raoult's law under all condition of temperature and pressure. We divide solution into two categories. One is the ideal, other is the non-ideal, right. Now, when we talk about ideal, I am just summarizing it again because we did this topic, but now we want to start another topic, and before starting that I want that you should be well versed this topic again, right. So, I am just doing in a short span of time, just look at the book. So, ideal solution is that which obey Raoult's law at all condition of temperature and pressure, you know that. And the non-ideal is one which do not obey the Raoult's law at all condition of temperature and pressure. Now, I told you the reason also, because in the ideal one, the interaction between the solute and solvent is just similar to the interaction between the solute particles and the solvent particles. So, let us say solute be A and solvent be B. So, the AB interactions are almost similar to the interaction between the AA and BB. But when we focus on the non-ideal one, the interactions are not at all similar. The interaction between solute particle is some different, the interaction between the solvent is different, and the interaction between the solute is different. So, that means the attractive forces or the interaction which is occurring between the solute and solvent particles and between the solute particles and the solvent particles are somehow different from each other. So, that means this ideal solution is going to obey Raoult's law. And what do you mean by Raoult's law? Raoult's law is something that partial pressure is equal to the product of the pressure exerted when it is in pure solvent into mole fraction, right. So, suppose this P1 is exerted by A, so this P1 is equal to P1 naught into X1, and similarly P2 is equal to P2 naught into X2. Right. So, that means ideal solution obey Raoult's law, so that means it obeys this thing also. And you know, when these kind of solute and solvent are mixed, when A and B are mixed, so as the interactions are similar, so that means the change in heat energy is going to be 0. There will be no change in heat energy, no change in enthalpy, right. And moreover, the volume is not going to change. So, this is what we did for ideal solution. Now, when we talk about its graph, like if we want to explain the behavior of ideal solution graphically, we draw it this way. You know this graph, I told you in the previous lecture as well, that let us say X1 is the A component and its mole fraction is 1 and X2 is 0, and this is the partial pressure exerted only due to the X1, right. Similarly, we did for the X2, in this X1 is 0, X2 is 1, and the pressure exerted by the X2 component, let us say it's P2 naught. Right. So, by joining this P1 naught and P2 naught, it will give the pressure, you can say the pressure which is existing when the A and B are just mixed to each other, or you can say they just give the pressure of the solution. So, that is P1 plus P2. Now, if you decrease the concentration of, like in this case X1 is 1 and the pressure is this, but if you decrease the concentration of X from 1 to 0, you will see that the pressure will fall down, right, because the pressure is just because of the mole fraction. When the mole fraction is approaching 0, so obviously the partial pressure that it would exert when it is present alone is going to approach 0. Likewise, it happens for P2. So, this graph is actually obeyed by the ideal solution. But when we talk of the non-ideal solution, what we get to see that as I told you, interactions are not at all similar, right. So, that means when A and B are just going to combine, the process can be endothermic, a process can be exothermic depending upon the interaction, that whether the interaction is more or whether the interaction is less when we compare with the solute or solvent interaction. Now, so that means it do not obey Raoult's law. So, that means this is not obeyed. That means the pressure it would exert in a solution is not equal to its partial pressure when it is present in a pure form into mole fraction. It is not equal to that, right. And moreover, as I told you that it can be an exothermic or the endothermic, the dissolution process. So, that means the delta H is not equal to 0. Either the heat is released or heat is absorbed. So, that means delta H can be accordingly positive or negative. And likewise, it will have the effect on volume also. There will be increase or decrease in volume. So, that means delta V is also not equal to 0. So, that means if we talk of non-ideal solution graphically, so that means this is not obeyed by the non-ideal solution, right, because in this case the P1 is not equal to P1 naught into X1 and the P2 is not equal to P2 naught into X2, right. So, that means we will see a certain kind of deviation. Now when we talk of the deviation, we will see that the deviations are of two types. Either the vapor pressure will increase or the vapor pressure will decrease. That means either it will have more vapor pressure as compared to the ideal one, and either it may have the vapor pressure less as compared to the ideal one. So accordingly we classify non-ideal solution into positive and negative deviation. If the vapor pressure increased due to some reason, we will be discussing now that what probably the reasons can be. So that means it is a positive deviation. And if somehow the vapor pressure decrease, so that means it is showing a negative deviation. So we are just starting with the positive and negative deviation. That means the non-ideal solutions, how they show positive and negative deviation, or what substances are added to it, or what are the reasons behind that they are showing different kinds of deviation. I have one example each for you. That is, positive deviation one is the ethanol and cyclohexane, and negative is acetone and chloroform. We will be discussing that how they are actually showing the positive behavior, or that means or you can say that how their vapor pressure is being increased and how in this case the vapor pressure is being decreased, despite that they both are non-ideal solutions, right. So just look at the board here. Now positive deviation. When I say positive deviation, it should be clear in your mind that in this case vapor pressure is going to increase, obviously, right. Positive deviation means that it is the pressure exerted is somehow more than the product of the the partial pressure of pure solvent into mole fraction, right. So that means the vapor pressure of the solution is increasing. Like on the whole what we can say that the pressure partial pressure of the solution is increasing in this positive deviation. And when we talk of this negative deviation, vapor pressure is somehow decreasing when we compare it with the solvent or solute. Now I will be discussing this positive deviation in detail, and then we will be taking up the negative deviation. See what happens in this case. Suppose I have this solute, let this A be my solute, and there will be AA interaction, you know that, right. And in this let it be my solvent. I will make solvent with circles. You can make either of forms, it is just for the explanation I am making. So let it be B, and it is my solvent, and there exists a BB interaction, right. Now I am going to mix them, right. I am now going to mix them up. So let us mix in this container, the third one. So this be solute and this be solvent, right. So that means if we talk about this, so let the mole fraction be XA and the pressure be P naught A, and in this case let the mole fraction be B and the pressure be P naught B. And what happens in this case now? In this case the total pressure is equal to P1 plus P2. It is equal to P1 plus P2 because both are volatile, right. So that means it is equal to P1 naught into X1 plus P1 naught into X2. It should actually happen like that. If it is an ideal solution, it should exist like this, as I told you here also. But now what is happening in this case? In this case, the interaction between the AA and BB is somehow of certain value, but when we mix them, there is obviously an interaction between AB. Right, because when you mix solute and solvent, there is always an interaction that holds A and B together, right. So that means now if we compare the strength of the interaction, what we found that AB is comparatively weak. That means it has a weaker interaction if we compare it with BB or AB. Now if the interaction between A and B is weaker, so what do you expect? What kind of behavior do you expect? Will the evaporation or the vapor pressure is going to increase, or will the vapor pressure is going to decrease? Obviously it is going to increase, because when there is weak forces, so that means they are free to get escape into atmosphere or into a vessel, you can say. So that means they will be escaping, and the escaping tendency will somehow increase. I will write here, escaping tendency will somehow increase because the force of attraction is weak here. So now when the escaping tendency is increasing, so obviously vapor pressure is increasing. Vapor pressure is increasing. So that is what I just want to tell you, that they will be having vapor pressure more than their expectation, expected if we compare it with the ideal solution. So in this case, if we write the expression for this, total P1 we know is equal to P1 plus P2. Now when we look for the expression for P1, so obviously P1 is not equal to this, it is somehow greater than the P1 naught into X1, because the forces between them are weak comparatively. And likewise for P2 it is greater than the expectation. right. So that means in this, the pressure of the solution, I'll write here total, the total pressure of the solution is going to increase if we compare it with the sum of this expected behavior, right. So that means it is just going to show a positive deviation. Now, as I told you that it is not obeying a Raoult law, that means this is not obeyed actually. The pressure exerted by each component in the solution is more than the expected. So we can say that the total pressure is more than the expected, that is the more than their sum. Now, when we talk of delta H, so for this kind of process, delta H is just going to be positive. That means this solution is endothermic. This solution is endothermic. It is going to absorb heat. And when we talk of delta V, so obviously it is going to be positive. Now, why delta V is going to be positive? See, because it has a weaker interaction. Weaker interaction means they will be loosely held, and when they are loosely held, so obviously volume is going to increase if we compare it with the ideal one. So that is why we say that they are showing positive deviation. So let me take one example in order to explain you. So let's say that we have ethanol. So what we get to see in ethanol, we get to see this kind of structure in ethanol. So that means there exists a hydrogen bonding between ethanol molecules. There exists a hydrogen bonding between ethanol molecules, as you can see. Now, when I am going to add cyclohexane, then what happens when I am going to add cyclohexane? It is going to occupy the spaces between the different ethanol molecules. So somehow it will result in the weakening of force. That means this hydrogen bond will get weakened, or you can say will break. And you know that when this hydrogen bond will get break, so obviously the strength is decreasing. That means the ethanol molecules will be combining with cyclohexane with the lesser force. There will be less force of attraction if we compare it with the ethanol molecules and the cyclohexane molecules. So that means it will be showing positive deviation. Now, if I want to show this positive deviation with a graph, how can I show that? So obviously it is not going to be this. So just look at in this graph. So that means vapor pressure is somehow going to increase. So what deviation will you found for this? So let it be this black lines indicating the ideal graph, and for non-ideal showing positive deviation, the pressure is just going to increase. Even the P2 is more and even the P1 is more than the expectation. So that means if we want to show the positive deviation, you have to show in this way. The main points are that the vapor pressure is increasing, escaping tendency is increasing. The reason behind this is the weaker force of attraction between the solute and the solvent. And due to this, the pressure is, you can say the partial pressure which it would exert when it is present in the solution form is greater than its pressure in the pure solvent into mole fraction. And likewise, the heat delta H is going to be positive, delta V is going to be positive, and moreover, you can say the vapor pressure is just going to increase. So this is how you are going to show when somebody asks you about the positive deviation. Now, let us see negative deviations. Now, what happens in negative deviation? In this, the vapor pressure is somehow decreasing if we compare it with the ideal solution. So that means vapor pressure decreasing means escaping tendency is decreasing. Escaping tendency will be decreasing, or you can say number of vapors formed is less. Number of vapors formed is less. What can be the probability? What can be the reason? Obviously, in this thing, what we get to see that the interaction between A, B are stronger if we compare it with the interaction between AA and BB. So that means the resulting solution which contains solute and solvent has more attractive forces, and more attractive forces means they are less free to get escape, right? So when they are less free, so obviously the less number of vapors, and less number of vapors means the low vapor pressure. This is what we get to see in this negative deviation. And if we talk about the total pressure, so obviously the pressure due to P1 is going to be less as compared to the pressure it would exert when it is present alone. And likewise, when we talk about P2, it is all obviously going to be less, same as in this case. So that means total pressure is going to be less as compared to their sum. Right, so that means the vapor pressure is just going to decrease. And when we talk about delta H, so in this case the delta H is going to be negative. delta H is going to, because more attraction leads to the release of more energy. So that means in this case the dissolution process is exothermic. And when we talk about delta V, so obviously it is clear that there exist more attractive forces. More attractive forces means they are tightly bound. Tightly bound means less volume. They will occupy less volume. So we can say change in volume is negative. And if example I am illustrating you, let us, as I told you, example of acetone and chloroform. So what do you get to see in acetone? You know that acetone is this and chloroform is something this. So what happened when you mix this kind of molecules, acetone with chloroform, there you can say their interaction becomes stronger because it leads to the formation of hydrogen bond. And you know that hydrogen bonding is increasing the attraction, so obviously the delta V is decreasing and even the delta H is negative, because now there exist more attractive forces. More attractive forces means less tendency to escape. Less tendency to escape means less number of vapors formed. Less number of vapors formed means obviously the less vapor pressure, which denotes that is the negative deviation. So in this case, if I want to explain it graphically, just look at this graph. As I told you, this black one is for ideal behavior, this green one is the non-ideal with positive deviation, and now I am drawing the negative with this red marker. So that means ultimately there will be decrease in the you can say the vapor pressure. So that means fall in this level. So that means this, sorry. So that means this is going to fall, even this is going to fall. So that means vapor pressure is going to be less than it is expected. So if somebody is going to ask you about positive and negative deviation, I think you can easily explain. Just start with the thing that you can say the vapor pressure is fall down and vapor pressure increase if we compare with the ideal solutions, right? And the reason is that you have to focus on the interactions, because the reason behind the formation of the vapor is just the you can say the interactions. When the attractive forces are more, obviously the escaping tendency became less, and when the attractive forces are less, so obviously escaping tendency increases. And likewise you have to just answer it accordingly, taking into consideration delta H and delta V, and likewise you will come to know that the vapor pressure is increasing or decreasing, and that you can show with this graph also, right? So this is our ideal and non-ideal solutions. Now we are